but maybe what he's best known for is his work on, he's the person who really started thinking about quantum algorithms in the context of lattice problems in a very deep way. And that led him to define this LWE problem, which of course is the central character in post-quantum crypto. And so today he'll tell us about something that brings lattices together with Shor's factoring algorithm. So Oded's really looking forward to your talk.
Great, thank you, Umesh. And yeah, I should say that I owe you a lot, Umesh, for support when I was there. In fact, learning with errors. I remember walking on campus, and while I was there, postdoc with you, and this is where it all started. So I'll tell you today about this efficient algorithm for factoring integers. And as I was saying before, feel free to interrupt and ask with if you have any questions. So let me start just by defining the problem, which I assume you've seen before. So we're trying to factor integers, and if you have 15, it's okay, 3 times 5. If you have 21, it's 3 times 7. 55 is 5 times 11. 1843 is a bit more difficult. 97 times 19. And this already gets more difficult. So 8051 is a number that I'll use as a running example. It's not as easy to factorize. And actually, there's a nice story that Carl Pomerantz shared. And this is his experience from a high school math contest. So he was asked to factorize 8051. And he was sure he can just try to divide. You only have to go up to the square root. So it's up to about 90. And he sure he could do it. But he thought, let's try to be clever, because surely there's a better way of doing it. So he tried, and he spent a couple of minutes trying to find this clever way, but then kind of got worried that he's wasting too much time. And indeed, he had wasted too much time, and he missed the problem. And this experience must have been quite kind of traumatic for him. And later he went back and figured out the trick. And the trick is actually, you can write 8051 as 8100 minus 49. So it's a difference of 2 squares, 90 squared minus 7 squared. And this you can just write in this nice way. It's 90 minus 7 times 90 plus 7, which is 83 times 97. So there's a very nice article he wrote about this in the notices of the AMS. I highly recommend this. And basically, this led him to develop some of the fastest known algorithms, classical algorithms for factoring integers, like quadratic sieve. So this idea was quite influential. This high school math contest experience was quite influential for him. So we know factoring integers is a difficult problem. Current world record is 250 decimal digits. I think it's like 800 something binary digits, maybe 840. And it took 2,700 computer years, so it's an extremely difficult problem. And this is really just something that we don't know how to solve using classical algorithms. The best known algorithm, number field sieve, is actually surprisingly fast. So it's a development of the quadratic sieve I mentioned before, but Pomerantz was involved in many of those things, and it's actually a remarkable algorithm, and it is remarkably fast, and yet it's not polynomial time. It runs in this exponential time in cube root of number of digits. So so it's able to do amazing things, but you cannot factor numbers with 800 binary digits. So it's not NP-hard, I should say. You must have heard this before. The problem is not NP-hard. It's a cryptographically hard problem. And secure communication, of course, is based on this. So cryptography is typically based on this. And we assume, we conjecture that factoring is hard. And that's how we build all cryptography, or that's how we used to build all of cryptography until recently. Okay. So this is where our story starts. In 1994, Peter Shor discovers factoring is easy for quantum computers. And I think that's what brought many of you to quantum computation. This is this phenomenal result showing that quantum computers can break all the cryptographic encryptions that that were used and at the time, RSA and then the curve and whatnot. So this is kind of a huge breakthrough and really worrisome, because it's saying basically we cannot use cryptography anymore. We cannot encrypt our email and bank and so on. But it's not really the end of the world. Okay, so don't panic yet. Well, partly because this transition that started recently, and some people here have been very involved in it. This transition to post-quantum cryptography started, I would say, in earnest last summer. And slowly, many protocols and instant messaging and the web HTTPS and so on, slowly switching, or maybe quickly switching, to this kind of post-quantum encryption. It's supposed to be based on other problems that are not factoring-like problems, and then presumably are not susceptible to this kind of algorithm like Shor's algorithm. Okay, so maybe it's not the end of the world. And maybe another reason why you would say let's not worry too much is because quantum computers don't exist. But that's something that is maybe more of a question mark, because it seems like they're coming, right? It seems like every day now we hear about bigger and better quantum computers, and there are issues, but it seems like progress is being made, and who knows, maybe in a few years we'll really have a big fault over in the quantum computer. So you've seen some of those news releases, and there's like one basically every week these days with more bigger and better quantum computers. That's this nice figure I stole from Sam Jack, and it shows where we are currently in terms of number of qubits and the error rate. That's as of 2021, I think. So things have keep changing. There are more qubits, better architectures, and so on. There are a bunch of other things happening here, which I don't know much about. And this is basically where Shor's algorithm starts kicking in terms of number of qubits we need, the error rate. So, I don't know how up to date this is, but basically just to convey the idea. The idea is we are trying today, try to tell you about an attempt to bring this down, right? Trying to find more efficient ways of factorizing integers. Okay, so this is kind of what we're trying to do. And hopefully, maybe the two ends will match or get close to being matched. And we can talk about this later during the panel. Okay. So without further ado, this is the main result. And at this point, again, feel free to interrupt with any questions. So let's go over it. It's actually basically saying there's the quantum factoring algorithms, but let's see exactly what the small print is saying. So okay, so there's an algorithm factoring n-bit integers. Okay, the way it works is that you need to have a quantum circuit. Okay, the quantum circuit has a relatively small number of gates. That's really the claim to fame. This is really the novelty here. The n to the 3 halves, instead of n squared gates in Shor's algorithm. Okay, so it's a smaller circuit. And then, it actually needs to apply the circuit multiple times. It's not like you run the circuit, you measure, and that's it. You actually have to run the circuit, measure, and then run it again independently, and measure, and then run it again. So you do it a bunch of times. You can do it in parallel. There's no dependency between them. You just do it a bunch of times. Each time you get a measurement, and you just have to then combine everything, do some kind of classical post-processing, and you get the output. You get the factorization. Okay, so this is kind of very briefly how this thing works. So again, if you just look at this, you think, okay, this is ridiculous because n to the 3 halves times square root n is also n squared. So what did I gain? But what I gain is that the quantum circuit itself doesn't need to be so big. So in principle, you don't need to keep it, maybe coherent for so long, or in principle, it might be easier, all else being equal, right? In principle, a circuit with fewer gates should be easier to implement. Okay, so before you protest, I'll discuss this more in the next slide, but this is the idea. We want to reduce the number of gates that we have to run in the circuit. Running the circuit later square root n times should be, should be okay. Should be something that we could just do. Questions so far? Oh, Ronald.
I have a question. Oh, sorry.
Okay. That's even better.
What's the mild theoretic number-theoretic assumption?
Yeah. So there's okay. Let me two small prints here, right? So there's let me start again with Mishafi's question. Mild number theoretic assumption. You'll see later where it shows up. Let me get back later to where it shows up. We need to assume something that Peter Shor doesn't have to assume. Later you will see where it shows up. I'm currently working with Igor Spolinsky trying to prove this, and I think we have maybe convinced ourselves that it's probably true, but we are still unable to prove it. We kind of know where what the reason is, or we have some better sense of where the challenges are in actually proving it rigorously, say based on something like GRH. So we are unable to prove it, not even based on GRH, but we have more confidence that this makes sense. It's something that I don't know, maybe number theorists will tell you should obviously be true, but certain things are kind of difficult to prove. You see where it comes up later. It's something about like small numbers generating the group of the multiplicative group. So again.
So if you're talking about the GRH, I mean, just by intuition, does this mean that your algorithm, you can prove that your algorithm works for some large fraction of the n-bit integers?
So that would be enough. I mean, I would be happy with such a result, like saying, okay, you cannot factorize all n-bit integers, but you can do it for a large fraction. But even that, I don't quite know how to prove. Yeah, this is a good point. Yeah, it's a good point. Even that, I don't quite know how to prove. Ronald.
Yeah, so this is a question about parallelization. You can think of your result as sort of partial parallelization of Shor's algorithm, but there's a much more extreme parallelization known due to Cleve and Watrous that says that you can do quantum factoring in like order log n quantum depth with polynomial time, classical pre and post processing. So I wanted to ask how this compares.
Right, so that's a great point. And I think I'm actually specifically at this point not mentioning depth. I will maybe mention it in the next slide. And I think in their approach, they really care about depth, right? So they make the circuit very shallow. The number of gates is actually much larger. So yeah, so it's a different trade-off. I would say if you care about number of gates, it depends on the quantum architecture. If this is really what you want to optimize, then maybe what I'm showing today maybe is the way to go. But yeah, this is highly relevant, right? If you care about depth, this is not the figure of merit that I'm really focusing on, and I should have probably mentioned that there's other work on optimizing Shor's algorithm in different directions. Yes, definitely depth. If you really want to minimize depth, you can do it. There's basically a nice way of parallelizing multiplication and so on. Yeah, very good point. Okay. So I should also mention this was extended to discrete logarithm. So what I'm showing you today is for factorization, but you can look at this. I think it's still a preprint by Ekara and Gertner showing how to do it for discrete log. And also, I should also say it's important. This numbers I'm showing here, this n to the 3/2, the n squared. It's just for convenience. I'm assuming that you have fast integer multiplication. So for those of you who care more about practical size, like 2000 bits, that's probably not too relevant, but you just have to scale everything up appropriately. So this would become n to the 5/2, so n to the 2.5. This would become n cubed. So everything proportionally scales up. So there's still the same advantage, even if you don't like to use fast integer multiplication. So for convenience, today I'll assume that we have near linear time integer multiplication, but the same thing happens. The same improvement shows up also without that assumption. More questions? Okay, so now let's maybe say a bit more about implications in practice. And I'm saying practice in quotes because I don't yet have a really quantum computer to test it on. So it could depend a lot on the architecture. If you have like superconducting qubits, if you have trapped ions, if you have neutral atoms, if you have optical, if you have so it depends really on the architecture you have in mind, and it's really a difficult question, right? So it's not clear. I'll be fully honest. It's not clear currently if it can improve on Shor's algorithm in practice, because I don't know what practice is partly. But also, Shor's algorithm is just generally amenable to very nice, very clever optimizations over the years. Some of them are applicable here, but others might not. So there's also a question of how much one can really optimize what I show you today. And again, Shor's algorithm is, in that respect, very good. You can really save a lot in many computation, memory, and so on. So it remains to be seen how much of that really transfers to the new algorithm. And I should also say this question of really seeing what are the resource requirements from an algorithm. This is a difficult problem, and you can look at this work of Gidney and Ekara. It's really tour de force that they take into account many parameters like space-time, noise, and to really see how many resources we need to implement Shor's algorithm. In principle, one might be able to do something like that here, but it's not obvious. It will take probably some time to understand what optimizations one can do. So, yeah, this is something I should say, and then that the one metric that's really important is actually memory usage and number of qubits you use. In Shor's algorithm, it's pretty amazing. Actually, I was surprised to learn this, that you can implement Shor's algorithm with only like 3n logical qubits, maybe even below if you really squeeze for qubits. But this is kind of amazing if you think about this, that you almost don't need to store. I mean, just storing the number to factorize is n qubits, and you can do almost with that 3 times that. So Craig Gidney is here, he can tell you more about this. There are some really remarkable optimizations you can do. The way I'll present today, the algorithm actually needs much more memory, needs n to the 3/2 qubits. But nice result of Raghavan and Vaikuntanathan show that actually you can improve that. And I don't know what the record is, but last time I checked, it was 15 times n. So it's also linear in n, similar to Shor's algorithm. The amount of memory is 15 times n. But it's still not quite 3 times n. So I don't know how much more this can be improved. But at least the memory usage now currently seems reasonable. Any more questions? Because there's much more probably one can say and should say about implications in practice, and we can discuss also some of that in the later in the panel. But if there are any questions, let me know. Otherwise, I will go to the more technical part of the algorithm. Okay. So okay, you can still interrupt and go back. But okay, so let's get down to business. So this is Shor's algorithm. At least how I think about it. And Shor's algorithm is all about finding periodicity, and this is one way to visualize it. Actually, I should say that I'm doing it a tiny bit differently. So if you watch carefully, you might see in the next slide, I'm actually doing the algorithm a tiny bit differently because that's the way I want to extend it. But it's not a big deal. So basically, Shor says, okay, let's take a function, exponentiation function. So it maps z to, in this case, say 4 for simplicity. I just take some base of the exponent. Shor takes a random number. For convenience, take 4 to the z, and modulo the composite that we're trying to factor. It's right, 8051. Okay. So what you're seeing here is basically if I'm using colors to denote the values of the function. So kind of you're seeing here like 4 to the power 0, which is 1, then 4. 16, 64 to 56, and so on. So basically, you're seeing all the evaluations of this function, 4 to the power z, and so it goes on and on. At some point, if you look carefully, you might see there is a period. So at some point, this thing, we know this must at some point there's the multiplicative order of 4 will show up. So at some point, we basically start repeating the same pattern, and it kind of happens here. You can see it happening here. Right, you kind of see the same pattern here, also showing up here. Okay, so if you don't see it, let me show you some fancy animation. So look carefully. I'm going to move this thing all over here, and ta-da! You kind of see the things aligned. So this is the period. Let's see it again. Because it took forever to align this properly. Okay, so this is the period of 4. Okay, so this is the multiplicative order. So, and from now on, basically, this is all standard, right? So the minute you find the period, and I should say, if you haven't seen this before, the way you do that, you compute in superposition the function 4 to the z, right? And you can do it with a quantum computer, and then use some quantum Fourier transform to extract the period. Okay, this is standard by now. So the way once you have that period, in this case it was 984. Once you have the period, you're just done. It was kind of standard number theory. Let me show you how to do that. If you don't remember, it's pretty standard. So having figured this out, so if the period is 4 is 984, you immediately know, okay, that, so what does it mean? It means that 4 to the 984 equals 4 to the 0 equals 1 modulo 8051. Okay, this is what it means to have a period of this function. But if you remember, I chose 4, and I chose 4 to be a square, because I can then tell you that 2 to the power 984. Okay, so I chose 4 to be a square of a known number. So I know 4 is the square of 2. So 2 to the power 984 is 1163 modulo 8051. I'm just computed that. But what's nice about this is I know that this has to be a square root of identity. Okay, why? Because if I square this, well, I get 4 to the 984, and 4 to 984 is 1 modulo 8051, right? This is how we showed, how we found, this is why we found 984. 984 is by definition a period of 4. So 2 to the 984 must be a square root of 1. And moreover, you can see, kind of got lucky, it's not a trivial square root. It's not 1. It's not minus 1, right? It's 1163, right? It's not 1 or minus 1 modulo 8051. Which means that this is a non-trivial square root of 1. And once you have a non-trivial square root of 1, you're done. And this is, again, this is well known in number theory, and let me show you why. Because if you write down 1163 minus 1 times 1163 plus 1, right? So now expand, and this is going back to Carl Pomerantz's insight from that high school contest. If you expand this, you get 1163 squared minus 1. But I told you 1163 is the square root of 1. So 1163 minus 1 is 0. 1163 squared, or minus 1 is 0, which means that 8051 must divide this times that. Okay, that's what it means to be 0 modulo 8051. And it's all very basic number theory. So, if you follow, great. If not, it's not very difficult, believe me. And then we can just recover a factor of 8051 by computing GCD. Okay, and the reason it's non-trivial is because 1163 is not 1 or minus 1. So neither of this can be 0 modulo 8051. Neither of this is divisible by 8051. So GCD must be non-trivial, and we're done. We got 83 using this GCD. Okay, so I'll do it again in a few slides for the new, for the variant, for once we go to the new algorithm. One thing to emphasize here, I should say, I use 4 just for convenience in this calculation, but Shor actually takes a random number. Okay, so that will come up in a minute. Okay, so if you've seen Shor, you take a random number. Okay, so what's the running time? What's the number of gates, I should say? Okay, what's the number of gates? And the most expensive step is, and this is well known, is just the function evaluation. Computing this exponentiation is the most painful, most expensive thing here. Everything else is very easy. The quantum Fourier transform, it's super easy. Initialization is easy. It's all very fast. This is the only thing that really takes effort. This is the classical function, right? But we have to compute it in superposition. How do you compute such a function? How large z needs to be, this is important to understand. Z, the exponent, needs to be high enough so we see a period, right? We have to see the period. And that means that if we're trying to factorize an n-bit number, if this 8051 is, think of it as a big n-bit number, the exponent has to go to something like 2 to the n, right? Just to be able to see the period. So clearly, we have to go to pretty high exponents, like 2 to the n, to be able to see periods. And how do we do that? Well, obviously, we don't just do a times a times a times a like that, 2 to the n times. This will never end. We use the trick of repeated squaring, okay? And using this repeated squaring trick, which I'll show you in the next slide, this requires n multiplications because we keep squaring the number with itself. So it's n multiplications of n-bit numbers. Or if I, again, assume fast integer multiplication, we end up with something like n squared gates. Okay, so each multiplication is roughly n, maybe n log n, and there are n multiplications, so I have n squared gates. And that's it. That is Shor's algorithm, number of gates. Let me just show you what repeated squaring does. You've seen this, but it's good to see it again because I have to modify it a bit. So if you want to compute maybe a to the 29, the way you do it, First you square, so you start with a, you square, you get a squared. You multiply by a, you get a cubed. You square, you get a to the 6. You multiply by a to the 7. You square, a 14. Square again, a to 28, and multiply by a, you get a 29. So the sequence of operations is determined by the bit decomposition, by the binary decomposition of 29. That determines the order of operations here. And the number of operations is basically the number of bits in 29. So it's n operations, so n multiplications. Okay. So that's basically it for Shor's algorithm. And now before moving on, you might think, okay, here's an idea. Let's try to make it faster. Let's try to make it faster by maybe not choosing a as a random integer like Shor does. Not just a random element, random n-bit number. Let's try to take a to be a small number, like 4, like what I showed you before. Let's take a to be 4. That initially might sound like maybe it's useful, but if you think about it for a second, you see that really doesn't really buy you much. Setting a to be a small number maybe makes the first operation here easy because squaring 4 is very easy. I can just compute it with a piece of paper. And maybe the second squaring is also easy, but very quickly here, you just end up with like generic n-bit numbers. So if you think about it for a second, each time you square, number of bits doubles. So maybe the first log n squarings, you will maybe be a bit faster, but you need to do n times squaring, like you have to square n times. So very quickly after the first log n steps, it's basically a generic n-bit number, and it doesn't seem like you gain much. Okay, so Shor takes a to be a random number. We can try to take it to be small, like 4, like what I showed you before, but that doesn't really seem to help us much. Okay, so let's see. This is something we'll use in the next slide, but we have to introduce another idea. So question before I move on. It's in chat. Okay. Good. So the main new idea is really this. Oh, it's a question. Okay. So the main new idea is going to higher dimension. And I'm showing you here two-dimensional picture. It will be more than 2 dimensions. We'll talk about the right dimension later. But for this talk, I'll just use 2 dimensions because they're otherwise very difficult to visualize. So we have now a function that's a bit like the previous function. It's kind of a multi-exponent, right? Previously, we just had 4 to the z. And now I want to do 4 to the z1 times 9 to the z2. Those 4 and 9 numbers, for now, you can think of them as being just maybe some arbitrary square numbers. Okay, we'll talk about how to choose them later. And I'm basically doing a very similar thing to what I did before. And now we get this picture. Now it's a 2-dimensional picture of evaluating this function, this multi-exponentiation function, modulo 8051. You see, as before, we have some kind of periodicity. Okay, you kind of see this shape here, and this is what's nice about choosing small numbers. It's very easy to see the periodicity because you have this region where the numbers are just small, but this is just for convenience here. So you see this region here, and you kind of see it's repeating here and here and here and here. So we have a periodicity. In fact, what we have here is like a 2-dimensional periodicity. It's what it's called the lattice. So there's a lattice being formed here. And again, if you don't believe me, let me show you again some animation. So let's focus on this period here. And I'll show this animation like last time and see if it works. Okay. Try again. Oops, no, now it's being stubborn. Oh, okay, here we go. Okay, I'm not sure if you could see. I'll try to do it again. Here. So okay, so if you can see it, the 2 things align quite nicely. So this is really a period, and the period is now 2-dimensional. So what did I gain? We'll try to see what we gained by this. One of the hopes here, maybe you can appreciate it already from this picture, is that the period, at least kind of in terms of some kind of Euclidean distance, is not so far. Like previously, I had to go to like 900 or something. I had to really go far. If you look at this here, it's not actually not that far in terms of some kind of Euclidean distance, right? Because I only have to go like 47 here and whatever, like 18 here. So it seems like the period in some sense got closer. which is not too surprising because I have like 2 dimensions to play with. There are many more options I can cover, right? But intuitively, this could be useful because if I don't have to go too far, it means I don't have to use very high exponents. So intuitively, it might be helpful because, as you saw previously, raising to high exponents is actually quite costly. So maybe I can gain something, by having this period much closer to the origin. Okay, that's the idea. It's kind of works, but we still need to observe a few things. It's not the full story yet. Okay. So let's just summarize the idea. And this is basically the same as what I showed you before. It's basically just this kind of standard number theory, but let's see how it works again. It's basically the same thing. We found the period, so it's 19,47. Okay, so it was, in the previous slide, it was basically here, 19,47. Everything repeats if you move by 19 on the x-axis and 47 in the y-axis. Okay. So what does it tell me? It tells me that 4 to the power 19 times 9 to the 47, because it's a period, it's the same as the origin. It's 4 to the 0 times 9 to the 0, which is just 1, modulo 8051. Okay. So what do I know? Just like last time, I immediately get a square root of identity. In this case, again, I chose 4 and 9 to be squares of a known number. So I chose 4 to be square of 2, 9 to be square of 3. So I immediately know that 2 to the power 19 times 3 to the power 47, this number, whatever it is, 6888, this number is a non-trivial square root of 1. Again, why is non-trivial? Well, just because it's not 1, it's not -1, right? You can see just because 6888 is a different number. And it's therefore a non-trivial square root of 1. Why is it square root of 1? Exactly kind of by definition. If you square it, you get 1, right? You get this number here. Okay, so we have a non-trivial square root of 1. And exactly as before, once you have a non-trivial square root of 1, you're done because you can just factorize. So you know that 8051 divides 6888 minus 1 times 6888 plus 1. And we can recover the factor by taking GCD, say with the first one. So we take 6887 GCD with 8051, you get 97, and we're done. We'll factorize 8051. Okay, so this is exactly basically as before. The only difference is now that we have this 2-dimensional periodicity, and really the kind of the $1,000,000 question now is, what did we gain? What, in terms of number of gates? Does it actually save you anything in terms of number of gates? Okay. So let's try to look at it a bit more closely. And I think to see this, you have to understand how the calculation actually works. And as before, the only thing that really matters here is this classical computation, which we have to apply in superposition. So all the stuff happening later, like QFT, is not really very expensive. And I should have said, maybe let me say now that just like in Shor's algorithm, you also have to apply some QFT at the end, and I'll get back to it later. So this is the most expensive step in the quantum circuit and computing this function evaluation. Okay, so you have DD is the dimension. In the example I had, it was 2, but maybe we should choose higher dimension. Later we'll see how to optimize D. So I have Z1 up to ZD, those are the exponents, and I map them to this product. I goes from 1 to D of AI to the ZI, modulo my 8051 or my n-bit integer. That's what we have to compute. The question is, how long does it take? So, we're in dimension D, right? So as I told you before, it seems like the exponents don't have to be so high, which is great, right? If you just think about this for a minute, you see that it seems like we only have to go up to exponent 2 to the n over d. Okay, so we only have to raise to power 2 to the n over d. And why? If you think about this, it's kind of easy to see by pigeonhole, because if you let each of the zi's go up to this number, 2 to the n over d, the total number of combinations that you explore is 2 to the n over d to the power d. So you actually end up exploring a volume in terms of number of possible exponent combinations of 2 to the n. And after exploring 2 to the n by pigeonhole, you will see a period, you will see a repetition. Okay, this is basically proof that in exponent up to 2 to the n over d, you will see periodicity. So we know that there's a period with relatively small exponents, not 2 to the n, only 2 to the n over d. That sounds like good news. Okay, so everyone okay with this kind of pigeonhole-like argument? Just because there are so many possible inputs, there are B things to play with, you'll just see a period because you're mapping to a range of cardinality 2 to the n, 2 to the little n. Okay, so we'll see a period. This sounds great, but still, how long does it take to compute this product? So each exponentiation now only requires n over d multiplications, because I don't have to do repeated squaring like n times, only n over d. It sounds great. Well, but I have to do it d times. I have to do it for each of the i's from 1 to d. So in total, it seems like I still need n multiplications. So it seems like basically we gain nothing. So again, let me summarize. It seemed first that maybe we gained a lot because the exponentiation doesn't have to go very high, only up to 2 to the n over d. So when I do repeated squaring to compute this ai to the zi, I only have to do n over d multiplications. But there are d of them, so I'm still stuck at what we had before, n multiplications like we had with Shor's algorithm. Seems like we didn't gain anything, but we did gain something. And for that, you need another observation. Okay? So here's the trick. And this goes back to Shafi's question. So the trick is that we actually need to choose the numbers a1 up to ad as small numbers. Okay, so in Shor's algorithm, the numbers ai's were just chosen randomly, the modulo decomposite. The trick now is that, contrary to Shor's algorithm, if here we choose those numbers, the base of the exponent, if we choose it to be small, we actually gain in terms of number of gates, and you'll see in a minute why. So for instance, you can choose them to be maybe like squares of the first d primes. You can choose them in multiple ways, maybe like 4, 9, 25, 49. We can talk about how exactly to choose them. But first, let's see why it's so nice. So once you choose those things as being small, and when I say small, I mean those are really small things because we're dealing with an n-bit domain, right? We're dealing with numbers like, in a modulus that's n-bit long. And if I choose those, and d is relatively small, so you'll see in a minute how we choose d, but d is maybe like, we choose like square root n. Okay, let me spoil it. We'll choose d to be like square root n. So the largest would be something like log n bits. Those are very small numbers. They'll be like log n bits. So the trick, the observation is now we can actually compute this thing we need to compute, right? This kind of multi-exponent. We can compute it using only n over d big number multiplications. So I'm emphasizing big number because we need to multiply n numbers, but most of them will be very, very small. And that's very easy, very fast. Like multiplying 4 times 9, I don't need n gates for that. But the key will be to minimize the number of big number multiplications. Okay, so as you'll see in the next slide, it turns out you can actually do that. You can compute this multi-exponent using only n over d big number multiplications. Each one, if we have fast integer multiplication, each one takes something like n gates, so we end up with n squared over d. So this is really where the improvement comes from, the idea that we can use small a's, small base of the exponent, and compute this kind of multi-exponent faster than the naive way and end up with this n squared over d number of gates. So at this point, I'm sure you have questions. You should have some questions. You can interrupt me, or I will go back to it later. Some things probably don't make full sense yet. And
can I ask a question?
Good.
Okay, so I assume you want to choose small numbers. You don't know how many small numbers are there, and so forth. I mean, do you need some sort of assumption on the distribution? I'm guessing that's where your assumption is coming in. So my question, So my question is this: so could you do things like, and maybe you do it because I didn't read your papers. I'm sorry. It might be in the next slide. Could you do things like generating integers in factored form so that you can get the effect that these are random integers, and they are in factored form, so they.
You mean the a's?
The a's.
Mm.
So not the n.
Yeah.
Okay.
Yeah.
The a's.
Sure. Yeah. So I don't know. I mean,
it doesn't mean it means again that they might be large factors, but then you get rid of them. I don't know.
Okay. I think I see where you're going. Let's maybe revisit this later, yeah, maybe you'll see where the issue comes up, but it could help, yeah. I think, so maybe just to answer your previous question is that really the minute you start insisting that those A's should be small, you end up into some number theoretic questions whether things like that can actually, see the period and so on. So we need to make sure that they actually generate, in some sense, most of the multiplicative group. And I can say more about this later. But really, this fact that I want them to be small numbers introduces some number theoretic, complications, or this mild assumption, as I said before. I can say more about this assumption later. But in Shor's algorithm, it's not an issue because the base of the exponent is chosen randomly, and then everything you can Shor proved everything rigorously.
So Oded, just a follow-up to Shafi's question. So maybe you don't need the AIs to be small, but they could be smooth, right? I mean, that's sort of what Shafi's saying. But that might change the conjecture a little bit, but it seems like that's still going to be a conjecture, right? That's what you're saying, right?
Well, yeah, it could be helpful, right? If they're smooth, yeah. I'm not sure. I'm not sure it will help you. But yeah, I mean, trying to get the ends to meet, right? Like what number theorists can prove and what algorithm need would be great. Yeah. So
but if it's an integer, random integer in factored form, you would expect that its largest factor, even without assumptions. I'm not looking for smooth numbers, just random numbers. Still, the factorization
would be pretty large, right?
Square root. Oh, half, you're saying?
Yeah, I'm not sure it buys you that much. There's a number of bits. I don't think it buys you that much. I mean, those are very small. Those are like logit bits. Those are really the first primes. So yeah, maybe there's a middle ground. Yeah. Okay, but let me just for the sake of we're kind of in the middle of the argument, let me try to complete the argument, and then we can revisit this. Okay, so just to again recap, the idea is that we want to compute this multi-exponent function because the period is really interesting, this period of the function. And how do we do this? So how do we actually do it with fewer multiplications? It's really an exercise, exercise kind of algorithm scores. Let me show you how it's done. It's similar ideas have been before in the context of like multi-exponentiation, but let me show you how it's done. There's nothing very mysterious here. So how do we actually compute this? So maybe the first observation is that if we have small numbers like our 4, 9, 25, those like the base of the exponent, we can multiply these small numbers using only something like d gates. Okay, so this is again just a basic observation that if you want to compute this, you want to compute A1, A2, A3 up to A8. You don't want to do it kind of serially. You don't want to do A1 times A2 and then times A3 and then times A4, because if you're doing it this way, the numbers kind of keep growing along with the computation. Like in the halfway of the computation, you'll have numbers that are d bits long already, and each additional multiplication will take additional d gates. So you end up with something like d squared, because it's like like arithmetic, like 1 plus 2 plus 3 plus 4 up to d. So you end up with something like d squared gates here. But obviously, this is not the way to do it. If you want to multiply numbers, you want to do it in a kind of a binary tree fashion, right? So you do first A1 times A2. It's very fast. Also really small numbers, like takes like log d gate. You do A3 times A4, again log d gate, and A5 times A6, and so on. And then you kind of combine the results, and it's you get this kind of geometric series, and the number of gates in total is only like d gates. It's kind of dominated. Well, it's actually the same, I think, in all layers. So you get something like contribution of d in each layer and only log d layers. So it's kind of standard calculation, and it's only like d gates. Okay, so again, this is a basic observation. And if you believe me that like, multiplying small integers is so fast, okay, it's only d gates. Now you can basically complete the argument. And again, this is maybe it's a bit confusing. You have to really kind of do the calculation, but let me give you some intuition why this is fast. And the reason this is fast is because you're really trying to do almost all the multiplications with small numbers, right? You're trying to minimize to the extent possible calculations with big numbers, because once you're dealing with big numbers, like n-bit numbers, each operation is costly, right? Each multiplication is, or squaring is quite costly. So the trick in this, what I'll show you now, is the trick is to really do almost everything you can, you do it with the small numbers, right? Remember, those a's have very small numbers, 4, 9, so and so on, 25, so very, very small numbers. So let me show how it's done. It's, again, some kind of repeated squaring, nothing very deep. And if I want to compute this, for instance, I want to compute a1 to the 13, a2 to the 9, a3 cubed, a4 to the 6. I start with, what, basically 1. All the exponents are just 0. So I start with 1. And each time I kind of introduce or I inject, the next sequence of bits based on the least, actually the most significant bits of what I am trying to achieve. So I'll multiply by a1, a2. Okay, so this is the first step. Then I square. So what happens first? I get like exponents of 1, 1, 0, 0. When I square, the exponents are 2, 2, 0, 0. Then I multiply by a1, a4. I get 3, 2, 0, 1. These are the exponents. I square. So each time I square, all the exponents kind of magically double, right? That's the thing about squaring. So 6, 4, 0, 2. I multiply by a3, a4. I get 6, 4, 1, 3. I square. I get 12, 8, 2, 6. And I multiply finally by a1, a2, a3. I get 13, 9, 3, 6, which is exactly what they wanted. And again, the important thing to realize here is this. Okay, so those things I multiply by, I basically deduce them from the binary decomposition of the exponents. Okay, this is where those choices come from. And computing those things like a1, a2, a1, a4, or a1, a2, a3 is very fast. It's only, this is really negligible here. It's only d gates each time. And the depth I have to do it is really just the size of the largest exponent. So I only have to do it n over d. Like the height of this thing is only n over d. So the total number of multiplications, like big number multiplications, like what's happening inside the square, inside this multiply, this is only n over d times that I have to do it, leading to the total number of gates of n squared over d. So that's the calculation. Again, these things are actually very cheap. Computing this a1, a2, a3 is, I do it separately. It's very easy, not so many gates. But dealing with those big numbers here is what's costly, but I don't have, the depth is not, the number of squarings I have to do is only n over d. So it's, it's not so costly. That's the idea. So again, it's really kind of an exercise. It's a bit tricky, if you have to maybe write on a piece of paper if you can't immediately see that. But trust me, this is what you get here. Okay.
So, Oded, quick
Yes.
question. Sorry if I
good point. Yeah.
So computing the partial products, right? I mean, it's very cheap, right? I mean, it's like n over d times d, roughly,
Yes.
right? But so even if you did it the way the sort of like the trivial way which you told us not to do, would it be problematic, right? I mean, it's like n over d times d squared, which is like n times d. Still seems reasonable.
Yeah, it depends on what d's. I mean, yeah, it's true.
Right.
For the choice of d, eventually, you're right. I mean, choice of d, I'll eventually use square root, and it's okay. But we'll talk about maybe using higher d later, and then maybe it will start.
Then it's worse. Yeah, right.
Yeah, but good. Yeah, it's a good point. Actually, might be enough for this setting of parameters. So at this point, some of you might feel uncomfortable because in the previous slide, I told you that this is the number of gates that we need. And you might wonder, based on this kind of asymptotics, you should really take d as large as you can, maybe n, maybe d should be n, and this will give you n gates. So where is this n to the 3/2? Where does that come from? And this is because there's something I did not tell you, something very important. Okay, so this is the very important missing detail. There's something that you should have told me and should have interrupted me, because when I told you that you compute this two-dimensional or d-dimensional function, you do QFT. One thing I should have said, I did not say, is how to actually extract the period after the QFT. This is actually an important step in Shor's algorithm, which is non-trivial. I mean, if you think of what's happening in Shor's algorithm, if you remember that, you do the QFT, you then measure, but it doesn't immediately give you the period. You have to do some additional post-processing. If you remember, continued fractions. And turns out that in d dimensions, you have to do some kind of d-dimensional analog of that. And what turns out to be the thing you need to do is run lattice reduction. So in d dimensions, you need to apply some kind of lattice reduction to extract the period from the measurements that you do. And in some sense, continued fractions, like in Shor's algorithm, is basically kind of the one-dimensional lattice reduction. So it's actually, the analogy is very striking here. I mean, it's really, you can really see the continued fractions in what I'm going to show you next, but in the language of lattice reduction. So more precisely, if I want to extract the period in d dimensions, turns out that you actually need to solve a d-dimensional lattice problem. But moreover, this is also why we need to apply the quantum circuit d times. So this kind of goes back to the main theorem. Unlike Shor's algorithm, where you only have to apply it a few times, even there's, with this initially, at least naively, it's not just once, for similar reasons. You need to apply it multiple times here because you want to get like a basis of a d-dimensional lattice. So you have to apply this quantum circuit d times. And if you go through the math, what really ends up happening is that this measurement of the quantum Fourier transform, it really gives you a vector in the dual lattice. And then you need to use lattice reduction to recover basis of the original lattice which you care about. So there's some non-trivial lattice stuff happening here, but it's something we have to do. Let me just mention, it's not like something you haven't seen before, in the sense that or something like that. If you go like to Simon's algorithm, right, one of the first quantum algorithms we teach, if you look at Simon's algorithm, there's something similar happening there, right? You're trying to find this hidden like periodicity in the hypercube in 0, 1 to the n, or 0, 1 to the d. And to recover that, you have to apply like the Hadamard transform and measure, but you have to do it d times because you have to span the whole orthogonal subspace and then recover the secret vector. So if you've seen recently Simon's algorithm or you taught it, you might remember something similar in the sense that you need multiple measurements to be able to recover the secret you care about. I mean, I don't know if it's really necessary, but it feels like it's kind of needed. Maybe there's a better way to do it that doesn't require applying it d times, but yeah. So long story short, this can be done using the LLL algorithm, but this introduces an important change in the calculation I showed you before. LLL is an approximation algorithm. It doesn't solve lattice problems exactly. And the higher the dimension, the more difficult it is for LLL to approximate. So the approximation factor scales like something like 2 to the d, right? So it scales exponentially with the dimension. So as a result, we actually need to use exponents that are beyond what I was telling you before. So before I told you, look, you just have to go up to 2 to the n over d, and that's enough because you see the period. But actually, because you have this additional approximation factor, you actually have to go a bit beyond. You actually have to use exponents that are 2 to the n over d plus d. So you have to go a bit beyond. And again, something like that shows up in Shor. If you remember, Shor also has to take multiple periods to be able to get a good enough approximation so you can use continued fractions. So it's something very similar happening here. And this is where this 2 to the d comes from. And now you can finally see the trade-off, because if you look at this n over d plus d, okay, n over d is because we have to see the period, and d is because of the approximation factor. But if you look at this trade-off, you see, okay, I should really choose d, at least asymptotically, I should choose d as square root n. And this leads to what I promised, the n to the 3/2 number of gates. And also leads to us having to run the circuit square root n times, because d is square root n. Okay, so this is the most important detail here that I was owed you. So this is at this point, I think I can summarize. The algorithm is basically this. So you choose some kind of base, exponent base, A1 up to AD. And you can just really choose them to be 4, 9, 25, 49, like squares of small primes. Those are all very small numbers. You apply the following quantum circuit, d times. So you compute this multi-exponent in superposition, right, over all those exponents, ranging from 0 to 2 to the n over d plus d. Again, I have to take this extra d for LLL to account for the approximation factor. On the result, I have this like big state. I apply QFT, apply the quantum Fourier transform, I measure. And each time I get an approximation to a dual lattice vector, I have to apply d times to get like a basis, and then we can use LLL to recover really a period, or actually all the periodicity I recover a basis of the primal lattice that I really care about. This is the picture I showed you with this period in 2 dimensions. That's what you recover, the periodicity there, and use this period to factorize n, like we saw before. This is standard number theory. That's it. So open questions, and many open questions. So reduce the number of qubits or the space requirements further. Currently it's around 15n. This is the work of Ragavan and Vaikuntanathan. And number of gates, trying to actually get an estimate, like an honest estimate of number of gates, really physical qubits. I don't know. This could be quite interesting, but probably not easy to do this calculation in detail. How exactly this compares to Shor's algorithm for something like, say, 2048. Trade-off with the classical lattice algorithms. That's something I think potentially quite interesting, because you can spend more time on doing the classical post-processing. If you want to factorize a number like 2048, many people, many governments would be happy to spend more time doing classical post-processing. So potentially you can play with this trade-off, do more calculations, better lattice algorithms, not just LLL, but more sophisticated lattice algorithms, like BKZ or even fancier things that exist today. And as a result, maybe offload some of the quantum computation to the classical post-processing. This could be quite interesting to see how this plays off. Maybe another more technical thing I could say, this is, okay, it's really kind of a technical point. The way I describe the algorithm now, it uses a uniform superposition over the exponents. And it probably works, but analyzing uniform superposition like that is a bit annoying. Actually, even Shor's algorithm has this calculation there, and it gets even more annoying in the dimensions. It's probably doable, but at least currently in the paper, the proof actually uses a Gaussian superposition. It's much nicer to analyze it this way. But I'm pretty sure it should also work with uniform superposition, but I don't know for sure. At least in practice, I think it would be much easier to implement it with uniform superposition. So that's something maybe to look into, like in terms of analyzing what happens when you just take exponents in some box, not in a Gaussian, but in some box. There's some nice questions about circuits failing, how to do it more robustly, and there's some work recently. Maybe we'll discuss some of that during the panel, because we're actually applying a circuit here square root 10 times, and what happens if a few of those things fail? How robust this is, and there's some recent work of that that maybe we'll mention later in the panel. And something that we already brought up before, the number-theoretic assumption. I think it would be very nice to prove it or show that it follows from GRH or anything like that. But I still don't know how exactly to do that. I know it would be really fantastic if something else can be said about that. Okay, I'll stop there. Thank you.
Oh, great. Thanks for that. That was great. Let's see, any questions?
Going over the chats, there were only some very good comments there. I see.
Anuj, you're unmuted. Feel free to ask your question. You raised your hand.
Yeah, sorry, I think that was by mistake.
Where is that? Anuj, did you want to?
No, that was my mistake, I think, he said.
Okay. Okay, so very quickly, I think you mentioned this, but continued fractions, or I guess it's like GCD or lattice reduction in two dimensions or something, or is it so? So here also, what you're doing is using it to recover exactly, right, the you're going farther out and recovering exactly a basis for the period again.
Yeah, actually, you get maybe I go back to this two-dimensional picture. You really get a basis for for the whole lattice. You get and even though I actually really only need one period,
yeah,
I actually get a basis. In this case, you will get maybe two vectors. Like this is one vector and this is the other vector. You get really a basis generating this whole lattice of periodicity. And yeah, maybe I can say one more thing about this. You might have noticed that I chose in my example before, I chose this one here, this period here, and notice one here, even though this one looks closer. And the reason being is that this one here, if you actually just calculate whatever that gives you, this actually gives you a trivial square root. This would give you like, I think either 1 or -1. Some of those periods might be, will be actually trivial square roots. So I think what we need, basically, the number-theoretic assumption is really kind of telling us that we will be able to find some non-trivial square roots if we look at this lattice. There will be some not too far away non-trivial square root. That's one way to understand the number-theoretic conjecture.
Mm-hmm. And then if there's one not too far away non-trivial square root, then there are many. That's not the hard part, is it?
Actually, I only need one. I think there's something interesting happening here in the sense that in sense you only need one, and the minute there's one, because you find the basis of all those things, you will find it. So it's okay, the minute I have one non-trivial square root, I'm done. I have a factorization of my
I see.
number.
Then there would be one in the basis, is what you're saying.
Yeah, exactly. So there's an argument that says, I think that's exactly what you have in mind, that if there's one short vector kind of nearby a non-trivial vector in this lattice, it will have to be also in my basis, because the basis generates all of them. So yeah, so there's an argument in the proof that says something like that. Exactly. Yeah.
Andrew, you have
thank you for the very nice.
There's two Andrews.
Oh, which
no,
I think the other Andrew had his hand raised first. So if you want to go first, the other Andrew, that's fine.
Okay, sure. So I guess one thing that I was curious about is, could these ideas also be used to give faster classical algorithms for factoring? Like it seemed a bit reminiscent to me of Pollard row, where you're also trying to find sort of the period of something like x squared plus 1n.
Honestly, I doubt it. I mean, because so many people tried, and I think those ideas feel to me like they're quite specific to the quantum setting. I would love that, but I think it's
I would think it's exactly the other way around. So all these algorithms come from the row method and the Pomerance and.
I think it's actually right. Actually, absolutely right. Like I would say, can we actually use, like, say, number field sieve? There are amazing ideas there. And actually, if you look at the number field sieve, there are some like lattices showing up, and maybe some of that could be used, but I was unable to do any of it. But yeah.
Okay. Thanks.
I guess the other Andrew, with you.
I'll be the other Andrew here. I really appreciated the pedagogical quality of your talk, especially using Pomerance's example of 8051 from his high school math contest that he, was inspired by, in your talk. I thought that was a very nice touch. My question was, you've shown that by thinking about things in this lattice way, you can succeed more efficiently, but it seems like it might also be useful in failing more efficiently as well. You might, sometimes when you get a trivial root, you can use that with pre-processing, post-processing, things like this to think more cleverly about how you choose your next number. And I was thinking with this multidimensional search, maybe you can get more information about how to choose your next trial more wisely if you happen to, accidentally choose a trivial root. I was wondering if you thought about this at all.
I see. No, I haven't thought about this. I'm trying to see. So basically, what might happen is that you run the whole thing. You get a basis of the dual. You get all those dual vectors. You apply lattice reduction, and you end up with a bunch of basically trivial square roots. Yeah, I wonder. I mean, I'm not sure how to learn really anything. I don't know how to learn anything from that. I mean, probably I would just try to change my my exponent, the base of the exponents, not to be those particular prime numbers. Maybe take different prime square numbers. Yeah, I don't know if you could actually learn something from that. It's a good point. Yeah.
Yeah, I'm just sort of putting my Bayesian hat on. I feel like there should be some information there. I don't know if it's completely useless or completely information free.
So I don't. Yeah, I don't know. It's a good point. I don't. Yeah, I mean, I have to think about what the exponents would be. But it could be that it doesn't give you anything. But yeah, I mean, I would have to think about it. It's a good point. Yeah. Maybe you can salvage something despite not. Yeah. Thanks. Thanks, Andrew.
I guess there's one more question, Danilo. Maybe can you talk?
Yes, I can post it. I already printed in the Q&A, but I can read it again. Can you hear me, please?
Yeah.
Yeah, something is popping up on the screen, so I thought maybe you don't hear me. Okay. Ecker and Gartner extended Oded's algorithm for discrete log problem, but for the multiplicative group of ZP, but not in general as it was the case for the Shor algorithm. Why? Because namely, there is no extension of this notion of small group elements that Oded is using to the elliptic curve groups. So any comments, any ideas how actually this can be extended to the small group elements of the elliptic curve groups? Maybe otherwise the elliptical curve people would say, okay, we are maybe still safe from this extension or improvement.
Yeah, excellent point. So I think your summary is currently probably correct in the sense that I don't think it's known how to use this for elliptic curves. I mean, of course, you have Shor's algorithm, but to use, if you want to use something like this algorithm, you would need a notion of a small element. And actually, I think they discuss it here. If you go to this preprint on the archive from Ecker and Gartner, they do mention it, and there's an issue, right? Because it's as long as but it could be that there is a notion of small element that I'm not familiar with that would make something like that work, but currently I don't know if something like that exists, that something that would allow you to do faster operations. Yeah, it's a great point. Currently, this does not apply as is to elliptic curves because we don't have this kind of small numbers that are very easy to multiply, right?
Yeah, thank you.
Thank you. Great point.
Great. Okay, so I guess let's move on to the panel now. So for that, if you stop sharing, we can set this up. So while the while the panel's being set up, let me just introduce the panelists. So first of all, it's a great panel. So first of all, we have Peter Shor here, which is very, very appropriate. He's obviously a giant in the field, not only responsible for algorithms for factoring and discrete log, but also quantum error correction and fault tolerance. So Peter, welcome. Then we have Vinod Vakutanathan, who is from MIT. He's also, he's one of my favorite cryptographers. So Vinod works on lattices, LWE, homomorphic encryption, but also he's increasingly working at the intersection of crypto and quantum. So welcome, Vinod. And our last panelist is Craig Gidney from Google. He's a team lead for the development of Circ, and he's also, I think, one of the world's leaders on resource estimates for quantum practical quantum computation. So, Greg. I thought we first get the views of the panelists about the talk. Any reactions, etc. So start with you, Peter.
Okay. So I don't really have that much to say. First thing is that I was really amazed when I saw Oded's result, because my view was that lattice reduction was really a very expensive operation and it didn't get very close to optimal. So how could you possibly use it to do better? But I mean, the idea is that you trade off and you only need to reduce the I guess, I don't think it's dimension, by square root of n using lattice reduction, and that gives you enough time to account for the inefficiency of lattice reduction, but still gives you a speed up over, the plain factoring algorithm. So that was a really nice thing. And the second thing is, I want to say, what does this mean for discoveries of other new quantum algorithms? I mean, that an improvement to this, I guess, nearly 30-year-old algorithm didn't come around until this year is really pretty amazing. I think it shows the difficulty of finding quantum algorithms. So the fact that nobody has found any other nice quantum algorithms for useful problems may be due just to the difficulty of finding quantum algorithms, or it may be because there aren't quantum algorithms for other nice problems. And I don't know which one the answer is. I really would like to know.
Vinod, with you.
Yeah, Oded, the second time I'm hearing the talk, it's just as if it's the first time. It's an amazing talk. So I guess one comment I wanted to make was about the noise tolerance, in a sense, of Oded's algorithm. It turns out several of us observed, including Oded, Martin Akera, his student, my student, and I observed that if you even if a constant fraction of the runs of Oded's algorithm is corrupt, in a certain sense, let's say it produces sort of random junk, certain noise model, you can still factor. You can still sort of error detect and correct and factor and so forth. So it's sort of the following kind of consequence that I found striking, which is, if you don't do any error correction at all to, let's say, Peter's algorithm, it can tolerate an error rate of 1 in n squared, just trivially, because it's n squared size circuit. And for Oded, it turns out that you can actually tolerate an error error rate of 1 in n to the 3/2. Again, because you in total you run n squared gates, but a fraction of the runs can be corrupted, and I can tolerate it. So it's a quantitatively sort of better error correction property is something that comes out of his algorithm. I wonder how much more you can do. Maybe this sounds preposterous, but what if a fraction of gates in either Peter's circuit or Oded's circuit is corrupted? What is the worst that can happen? I mean, does a factor still fall out magically? Or maybe we can do slight bits of error correction without going to general fault-tolerant computation and still recover a useful factoring algorithm. That's open, but I found this noise tolerance angle interesting.
Sorry, I didn't quite catch that. So are you saying that each time you run it, you're recovering something, a dual vector, and if a constant fraction of those are not correct, you can still recover?
That's right. That's right. Exactly.
And can you say a word more about why that's okay?
Because somehow Oded's algorithm for post-processing, it sort of finds sort of linear combinations of dual lattice vectors that that do something, right? If you have one like random vector, very noisy vector, the chance that it participates in such a nice linear combination is pretty small. So you can use that to design a filtering algorithm that sort of, filters out all the noisy vectors. This is assuming that the noise has a certain form, that it is sort of uniformly distributed. So either you get a vector that's close to the dual lattice, or you get a uniformly random vector in the parallel pipette. So that's the assumption. You can relax this assumption a little bit, but yeah.
I see. And so, sorry, before, can you also comment a little bit about the space efficiency and how that works?
Right. So let me sort of comment about it in connection to, I think, Ronald, who asked about the depth of the circuit, right? These two seem connected to me, right? So in particular, the way you get depth efficiency for Peter's circuit is to say, the base is fixed, right? I mean, I pick a base A that is fixed, it's classical. So I can pre-process all powers of A squared, A to the 4, etc. That takes a lot of depth. It's sequential, but it's classical. So I can do it on the side. And then all I need to do is multiply. I can do it in a multiplication tree. So that contributes to the depth efficiency, right? And then you have to make the QFT low depth, and that was Cleve and Waterous. Yeah, they did that, right? And Coppersmith is the approximate QFT. So that's a separate story. It also contributes to space efficiency because you don't need to do squaring coherently to run Peter's algorithm. And if you were forced into that situation, you'd be in trouble because squaring is not a reversible operation. So I have to write it sort of in separate registers. Right. So the fact that you can pick the base once and for all and classically, and you can pre-process seems to contribute to both the space efficiency and the depth efficiency of Peter. Both those go down the drain, with Oded's algorithm as it stands. It turns out that you can recover the space efficiency in the sense that you can get an algorithm, you can get a circuit with n to the 3/2 gates and n log n qubits of extra space of NCLS. Or you can get n to the 5/2 and sort of Oded's at 15 n qubits. It's now 10.32 n qubits. And if my student, what he said is correct, a couple of days ago, it's 9 n qubits. And so the idea there is instead of doing squaring, which is not reversible, so I have to write the values in a separate register, you do exponentiation slightly differently using the Fibonacci representation of numbers, so the so-called Zeckendorf representation of numbers. So you have A, right? So A squared, you write it in a separate register, but I don't want to square that further to A to the 4 because I have to write it in a separate register. I do A squared times A, so I get, that's multiplication. So that's a to the 3. I can do a to the 3 times a squared, which is a to the 5. This is all multiplication. I don't do squaring. And if you look at the numbers, they are Fibonacci. So all I need to do is to write my exponent as a sum of Fibonacci numbers, and voila, that's that. This is an old trick discovered in the reversible computation literature, but we sort of like repurposed it here. Yeah.
That's very nice. Thanks for that. So, Craig, would you?
Sure. I mean, I agree with Vinod that the extra fault tolerance is very important. Like this property where not all the shots have to succeed is actually needed for what Oded was hoping for in his talk, where he says, it's easier to run a smaller circuit. If you have to run many small circuits, but they all have to work, like, for example, if you're taking statistics for chemistry and you don't know which shots are good and which are bad, then you need all of them to be as reliable as if you've done them all at once. Otherwise, it just doesn't work. So like that addition to the work from Vinod and his student, I think is like very important for this algorithm working. Like that is what would allow you to reduce the codistance of the logical qubits. Without that, you can't. I don't know if I have anything else specific to say without being prompted. I mean, I'm happy to take questions and such.
Do you have any thoughts on whether this would provide speed, some improvement?
Yeah.
So what sorts of architectures, or what?
Yeah. So there, in general, in quantum computation, there are an enormous number of ways to trade space for time. But often they are sort of a like one-to-one trade-off, and they have a sort of character where they're, I don't know. The thing that's interesting about this algorithm is it's a very different kind of space-time trade-off. It's a very high-level space-time trade-off instead of a low-level one, which is maybe what I'm more familiar with, where you use, for example, gate teleportation to do things in parallel, so that you need more space but use less time. So I kind of hope that this different space-time trade-off, then you can then use other space-time trade-offs to sort of move to where you want to go. So in particular, I often think in terms of what's called area time or hardware time or space-time volume, which is the amount of space you need times the amount of time you need it for. So you can think of this as a proxy for the energy consumption of the computation. And it turns out that a pretty good proxy for making a computation better is just to reduce the hardware time and then worry about packing it into space. So this algorithm actually technically doesn't really reduce the hardware time if you only look at it in the abstract circuit model, because it saves per shot, but then adds that same number of shots back. But because of this fault tolerance property, it could be 30 times noisier. And rule of thumb, if you're using surface codes, for example, is a D by D patch. If you increase D by 1, you get about 3 decibels more of suppression of noise, so about a factor of 3 less noise. So 30 times more noise tolerance means you can reduce D by 1 3 times. So if you were using distance 26, then you instead use distance 23. And so the amount of space that you would need, assuming everything else is equal, would improve by a factor of 23/26 squared. And this would also improve the time a little bit because your distance is also time-like. Anything else?
There's a question I believe for you from on the Q&A, maybe also for Oded.
Comment whether Oded or Vinod, can I comment on whether Oded and Vinod's improvements can be done in an iterative manner, at least on the control qubits? So I don't know the answer to that question. Actually, I have a question on the Quantum Stack Exchange, which has part of this question in it, that if anyone wants to answer, they can go try to do it. In particular, when we do phase estimation, and Shor's algorithm is doing phase estimation, we're typically doing it with phase oracles or phase operations that are powers of 2 of the thing we want to estimate. Whereas in this modification that Vinod has, we're using Fibonacci powers. So instead of getting the phase and twice the phase and 4 times the phase and 8 times the phase, we're getting the phase and 2 times the phase and 3 times and 5 times. Fibonacci multiples. Or sorry, I should have said powers. This breaks the normal qubit recycling circuit, but it doesn't seem like you shouldn't be able to do it anymore. Like, it seems like it should still work, and someone just has to, figure out the details. I don't know how to do it personally, but I feel like if the right person looks at it, they'll just know the trick. And like someone who's familiar with doing adaptive QFTs or something will just know some basic theorem that makes it work. Well, I should also say there are multiple obstacles here. So the algorithm sort of runs in 3 phases. First, you generate the exponents with these Gaussian distributions. Then you perform these like iterative multiplications in order to get the product. And then you do the QFT in order to estimate the phase. The problem I was just describing refers to the last part. So can we do that part iteratively? There's also the first part. Can we do that part iteratively? And Oded in his talk mentioned, can we use uniform superpositions instead of Gaussian superpositions? That would be a very useful property because a uniform superposition can be generated 1 qubit at a time with plus states instead of needing them to depend on each other. And then in the middle, I don't know the exact details of your implementation, but if you're using 2 accumulators and multiplying them back and forth and multiplying into one or the other as you go, then you end up with too much information at the end where how the bits are spread between the 2 accumulators could, in principle, allow you to decohere in a way you're not supposed to. So you have to measure their product and then uncompute them. But this means you have to do 2 passes over the exponent qubits, one to compute, one to uncompute. So you need some sort of obliviousness property where you don't know which one you're multiplying into, or it doesn't matter which one you're multiplying into. For example, the coset representation of integers that Zalka introduced, which makes this big superposition with a bunch of offsets by n in order to do arithmetic modulo n, that's introducing an obliviousness property such that additions don't reveal how many factors of n they've moved over. And we would need, I think you would need something like that in the middle. So there's 3 separate problems. There's this initial state problem, this obliviousness problem in the middle, and this iterative qubit recycling problem at the end. And if all 3 of those were solved, then you could probably stream it instead of having to keep the exponent registers around the whole time.
Oh, great. Thanks, Greg. Oded, do you have any thoughts now on the comments?
Nothing very specific. I would say, yeah, I think it would be interesting to see how much this can be pushed further. And one thing maybe to consider that, I've been discussing with others, imagine you just want to show that you can get some non-trivial information from this. Could this be kind of some, not for actually factoring big integers, but you just want to show that for medium-sized numbers, I don't know, like 200 bits. You want to show that the algorithm is doing something. You want to show that you get some signal after the QFT. So if it makes sense, like, you don't, like doing some near-term quantum computer demonstration, would this actually give you any advantage over, say, Shor's algorithm? Because if you think of the extreme, maybe you don't even have to do any exponentiations here. You just have to multiply a bunch of small numbers, modular exponentiation, and it's not maybe enough to really factorize, because, like, if you think of what you get in the measurement after the QFT, is very noisy. But maybe this is like in the bare minimum that you can still see some signal after you measure the QFT. So I'm trying to think if this actually can lower the boundary of where we can see some interesting quantum phenomena that points at something actually factoring. So if it makes some sense, I can try to make it more precise, but I haven't really thought about this.
Did you mean try to make it more precise now? Please do.
Yeah, maybe I should not volunteer that, because I should really think about this more. One can try to write down similar analysis, but really take things to the extreme where don't exponentiate or take very, very small exponents, and try to see if there's anything you can recover from the QFT. The thing here is that you really need to see the period, just like in Shor's algorithm, right? You need to make sure there's the period. But here, in some sense, the period actually shows up very early, right? You don't have to exponentiate much to see the period. It's only about multiplying the small numbers. And if you have n of them, some very small numbers, locate-bit numbers, just start multiplying them, you start seeing some period, but it won't be as nicely structured as we need to apply LLL and get good accuracy measurements of the dual vectors and so on. But maybe it's enough to tell us, okay, something is going on. We see something here that the quantum computer is actually doing. So, yeah, so that's just an idea.
Yeah. There's a question from Ike.
Hi, it happens my question's right along the line you were just describing, Oded, which is in your work, one of the great things you have done is to show the power of purifications for understanding a lot of properties of lattices and proofs. And it occurs to me that in your algorithm and construction, there's one big part you could purify to try to maybe understand the factoring problem better. which is the post-processing. What would happen if you had a coherent post-processing algorithm, a coherent LLL, a quantum LLL, and imagine you have a really big quantum computer with lots of them all running different versions of your lattice, and then coherently post-processed. Do you think that might give us some understanding of the factoring problem?
See, so currently the post-processing is separate, which allows you to break the quantum computation into separate circuits and then bring them together. If everything is done coherently, at least in terms of number of gates, you actually don't gain much.
Oh, absolutely
but
not.
You're right.
I'm not interested in anything practical. I would be interested in understanding the nature of the problem. Because I would want to understand what LLL or any kind of lattice reduction is accomplishing in a coherent manner. What is it throwing away? What is it keeping? How is it compressing some entropy in some places? I don't think we actually understand that. And then therefore we can't actually move far intellectually maybe on that last line of thought you were giving. Where are these small periods going? How are we throwing away some of that information? Totally impractical, but just a great deal of fun to think about.
Yeah, as you know, I really love this connection between lattices and the quantum. So if LLL can be used somehow, this would be fantastic. But
so I just to understand your question, right? If you run Oded's algorithm once, right? I mean, you get a superposition over the dual lattice or close to the dual lattice, right? So it's sort of the state has, and you're really kind of sampling many times from the state, right? So you're saying run it once somehow, and then something, right? Sort of like an LLL-like run an LLL-like algorithm coherently.
Yes,
on the superposition without matching.
That's right. It might need multiple instances of this run because there is some classical sampling you're doing also, but I'm not sure. And it would be wonderful to find out if there is a quantum version of the post-processing that could run just once.
Yeah, right. Okay.
That's even more speculative than what I'm asking for. But basically, I'm wondering, have any of you thought about what it would mean to have a coherent lattice reduction algorithm conceptually?
I haven't.
I mean, I was thinking about this, Peter, when I was reading your recent paper with Roger Lin, I think, from Harvard, because you have a new lattice reduction algorithm for specific kinds of lattices constructed from codes, and it's based on Euclid's algorithm, and we can make a quantum version of that Euclid algorithm. It's much simpler in nature than LLL, perhaps.
Yeah, well, thinking about doing, I guess, the lattice reduction or the continued fractions coherently really scrambles my brain right now, so I can't give you an answer.
Maybe an anecdote on the notion of running Euclid's algorithm coherently, which is there's this result where the GCD algorithm is one of the few things we don't know how to parallelize at all. And you think about it, if I can do period finding, then I could do period finding on the GCD, and you work through all the steps, and you get to the end and you measure it, and you're like, oh wait, now I have to do the GCD in order to get to do the least denominator estimate. It all falls apart.
But wait, potentially a GCD of randomish numbers, right?
Yes, that's true. It might be a different GCD.
In that sense, because of that anecdote, I've long thought of this continued fractions as a secret extraction algorithm. So I've thought about it as almost an adversarial scenario. And maybe that's what the quantum can do here, find this certain kind of secret that's encoded, the two integers.
A secret being the GCD?
The secret being which integers are closest to the given floating point number. So, right.
Is there something specific about the GCD that makes you think about it that way, as opposed to like thinking of a sorting algorithm as finding the secret sorted order of the inputs or something?
Mostly the connection of the generalization to lattice reduction, because there we explicitly think about secrets.
Okay.
And I don't know why there shouldn't be a physical process which allows us to accomplish this. There should be a Hamiltonian for LLL.
Well, maybe we can think about this offline, Ike.
Yes, thank you.
Right, thanks, Ike. So maybe I'll just see if there are any final thoughts from the panel.
On the question or in general?
In general, yeah, just to sum up.
On Vinod's comment about maybe we can have errors within the algorithm itself, I would be very surprised if you could survive poly-type errors, like you have a phase flip or a bit flip halfway through the algorithm. If you just, try examples of that and see what they do to the QFT output, it tends to be very bad.
Yeah.
On the other hand, we actually intentionally approximate the algorithm a lot already. So for example, in the QFT, there are all of these extremely tiny phase angles. And I think people's initial inclination upon seeing them is that they must be very important if we're writing them out. But very quickly, because each of those angles is twice as small, they get to the point where by linearity, they don't matter anymore. And so we don't do any of those. And that's probably a good example of where the errors don't matter.
Right. So I guess the QFT seems error tolerant in that sense, right? But we have already squeezed enough.
Yeah.
Out
The
of
other,
it.
the other thing is this point made by Zalka that that we've used, where because we're in this enormous superposition of many different integers, if you have an arithmetic circuit and the arithmetic circuit has some small proportion of inputs that it gives the wrong answer to, as long as you can show that proportion is small, as opposed to a bit flip where the proportion is 50% are wrong or 100% are wrong, then basically it'll still work. So if you only mess up one out of every trillion cases, unless those somehow correlate with the ones that are actually dominant in the superposition, then it's just fine. So like, for example, if you increment the register, there's 2,000 bits to propagate the carryover, but after 50 bits, it's almost definitely not still propagating. And so you can just stop. And it turns out that this sort of thing is okay, as long as you're not going to do it, to the 50 times.
So people should be looking for approximate arithmetic.
Yep.
And not exact arithmetic, and see if that reduces the number of operations dramatically.
Yeah. In fact, we do that. And the question is like, can we do it better? Or are there other places where we can approximate, or where something is preventing us from approximating and we could fix that and then approximate more? Actually, you don't even really need to know the quantum part in order to kind of do this problem. You can think of it as, I need to compute this value on a secure chip, and I have the ability to remove values from the secure chip by measuring them. And as long as an adversary that learns all those measurements can't figure out what I was computing, then it's probably safe to do it quantumly as well, coherently. So if you can bound the adversary's probability of learning the value below 1 and 2 to the 50, then the algorithm will probably work fine coherently.
Great. Shafti had a question.
So my question is about the elliptic discrete log, if elliptic curve discrete log, if there is any work that has been done on it, or in the context of a quantum, I guess, in your improvements you did.
Yeah, so beyond what I mentioned, I
Can
don't
you
think
remind
much.
me?
So yeah, so basically there's been an extension to discrete log, but not for elliptic curves, because you're really missing this notion of a small element, something that's very easy to apply group operations to. But if such a notion exists, I know that there's no reason why something like that should not work, but I don't know if the notion really exists. So if if you're doing discrete log in modulo, like in the multiplicative group modulo prime, this is easy. I mean this was shown to be possible, but for elliptic curves, I just don't know yet.
Great. Anything else? Any other thoughts? Otherwise, maybe on that.
The question that Ronald asked in the very beginning, right, about the depth of that circuit, can you sort of compress it? I mean, it's a problem that's begging for for someone to put it out of its misery. It should be possible, but we don't know how to. Yeah.
I just want to make one comment. So the reason I was asking about elliptic curves is related to the question I asked in the beginning of your talk about whether you can do your analysis for random numbers rather than worst case and get better results, maybe without an assumption. And maybe for elliptic curves, it's all intuition. I mean, that would be more likely that you could do an analysis. Like you could talk about the order of the curve, like the number of solutions, and that sort of is distributed nicely. And then maybe you can argue through that an algorithm could work for some on the average, not in the worst case. I don't know. I thought.
Yeah.
Maybe
We have more freedom with the order being a random number. This in terms of its factorization.
Maybe on the other question that the remark of Ronald and that we not just talked about, you can actually make the circuit constant depth if you have a fan-out gate. So you can even make it even less, use less time than the log depth. But there seems to be somehow a time-space trade-off here under the hood that I'm not sure we understand exactly how it goes. And Oded's result seems to be in somehow another region of this time-space trade-off. And in order to make it constant depth, you have to do actually some classical computation in the middle of your circuit, which you sort of don't count for. And there's some parallel because Oded is doing some classical calculation at the end of the computation.
So
it's sort of the interplay between classical computation and quantum computation, and somehow minimizing the quantum resources. Right, that's the game that we want to play.
Yeah. So Harry, can you remind us about the best time-space trade-off known for this?
Well, I know that the best. I mean, so I've been looking recently at making these circuits constant depth, sort of having sort of in my mind minimizing that, because that minimizes the amount of time that your circuit runs, and that should be beneficial for the buildup of errors. But unfortunately, you need more qubits for that. And I think I don't know actually what the number of qubits are, but they are getting beyond quadratic. I'm afraid, at the cost of, but at the gain of making your circuit constant depth.
So Harry, one of the properties of Shor's algorithm is that it has so much flexibility in the depth because it's just doing a modular exponentiation, right? Like you just do all the multiplications in parallel, and within the multiplications, you do all the additions in parallel, and it gets down to polylog depth, where we use currently, quadratic or cubic depth. And like essentially, the more qubits you can throw at this problem, the faster it will go. And essentially, it's almost a one-to-one like linear relationship where if you throw twice as many qubits, you get about twice as much speed for a very, very long time until your like computer covers a city or something, depending on the initial size scale. Although I guess you probably start running into decoding issues where the classical computer has to communicate quick enough to share the information that's being teleported all over the place and whatnot.
Exactly, yes. That's sort of the limiting point.
I think the limiting point is actually building the city-sized computer, but yeah. The surface code does have these great properties, or error correcting codes in general, where you can very quickly get entangled copies of information in very many places if you physically had the ability to do operations between them by establishing entanglement and doing swapping, right? But I think these things are sort of unrealistically large.
So Harry, just to understand what you said a little better, so the sort of the improvement to constant depth you were talking about refers to Shor circuit, right? I mean, you're saying you can actually, yeah.
Absolutely, yes, it is that. Yeah, it's not at all Oded's work.
Okay.
No, it's old. I mean, it's not my results, but
right.
It comes from the fact when you look at Hoyer and Spalek looked at this early on. When you have fan-out gates, you can really reduce the depth from logarithmic even to constant.
Got it.
And then there's a realization that this fan-out gates, you can get it actually by having sort of intermediate measurements and doing teleportation tricks and so on.
Thanks.
On the topic of constant depth, there's a lot we don't know about quantum circuit construction. And I think a really good example is classically there's a thing called the carry-save adder, which uses a special representation of a number where you can perform addition in linear space and constant depth. Basically, you just don't propagate the carries and you treat them as a second integer. And instead of doing addition that takes 2 integers and produces 1, you take 3 and produce 2.
Yeah.
We don't know if quantumly there is an equivalent thing where you have some special representation that has constant depth in linear space to do addition. We know an n times log of n version. The issue is with using the carry-save adder just directly is if you keep adding 0 into it, the carries propagate away, which means it's not reversible. So you'd have to fix this somehow. Anyways, this kind of knowledge is the sort of thing that you could, I mean, I don't know if you'd actually end up using this in factoring, but this kind of knowledge is the sort of thing that we need in order to improve the implementation of these algorithms. Like, I think most of the improvements to them are from realizing there are better ways to do arithmetic. Like, the reason Oded's algorithm works is because of this reordering what you're squaring thing so that you keep adding in small multiples instead of big multiples. That's not a quantum specific idea. That's a very classical sort of idea, but it applies in this quantum context. And I think a lot of the big optimizations are like that.
Well, on that note, shall we call it? Well, next.
Well, could I'd like to ask one last question related to this comment about representations to Oded. You know, residue number system representations do have this feature that you can do certain kinds of arithmetic very quickly. And I was wondering if you thought about that at all in the context of this lattice-based formulation. Maybe it would allow for further optimizations.
Yeah, I haven't. I think
you could add and subtract and multiply numbers in this representation without having to carry. You know, you just store the number mod a bunch of moduli, and then you just have to add them digit-wise or multiply them digit-wise. And so it makes the arithmetic very quick. The cost, of course, is that you can't do division quickly, and it's hard to tell which numbers, which other number.
Yeah, there's a paper that just came out recently that tries to use this idea. Yeah, you do run into this issue where you can't really do the modulus operation. And because you don't know the factors of the number, you can't pick the primes you'd want. So you need to pick enough primes to store the result without modding by n. where each individual product you're multiplying in has been modded by n, so it's not like it's getting incredibly huge. Anyways, in this paper, what they do is they compute these prime mod things one by one, and like kind of add up their contributions to a particular place in the output in order to try to get one bit of it instead of getting the whole thing. And I don't know if the paper is correct or not. I haven't really read it closely enough. But that's, I don't know, that's a very interesting idea. They have the downside that they have to keep the whole exponent register coherent instead of, so they've made the accumulator register much smaller because they only have this small prime at any one time and this small bit that they're accumulating. But they're doing many, many passes over the exponent qubit, so they have to keep all of those coherent, and there's usually more of those than there are in the accumulator. But it kind of moves the space cost around, and I don't know, maybe someone could find some interesting combination of this and Odeds or some other things where, you know, you get the square root of space or something.
Great. So
there is, well,
yeah,
there are questions in the Q&A.
Yeah, is there anything burning? Because of, no, let's see.
One of them that I think is interesting is, are there any barriers to getting the size of the quantum circuit to be O of n instead of O of n to the 3/2?
Oded, maybe that's directed at you.
Right. So maybe I don't have an answer, but I can say that if you're willing to spend more than polynomial time in classical post-processing, then you can actually reduce it a bit further. I don't know if I mentioned this before, but yeah, to truly get it to linear would be fantastic. It could be maybe understanding what's really happening in the Lattice problem might allow us to improve things. I don't know, maybe Vinod thought about this more than me.
No, somebody actually asked, you know, the same question, I think, in the chat. And you can do the obvious thing, like, you know, like I said, if you wanted you know, the classical post-processing to run in time slightly better than number fail-safe, then you can reduce the quantum circuit size. But yeah, I don't have anything else to say.
Or if you believe that lattice-based cryptography is broken and actually it's very easy to compute lattice problems, then you do get linear time quantum factoring algorithms.
That's interesting, isn't it?
That's something Yael Kalai called like a lose-lose situation. Basically, you both lose lattice-based cryptography, and you also lose well, you lose even more. You lose factoring-based cryptography because you can break it in quantum linear time, so it's a lose-lose situation here.
Great. Okay, so Oded, thanks for great talk, and thanks Peter, Vinod, and Greg for a fascinating panel. So and of course great questions from the audience as well. And I guess see you next time. We'll announce the next colloquium soon.
Bye, everyone.
Bye, Peter.